Alright, so today we are going to talk about polynomials. So we want to start by making sure we understand what a polynomial is. So if we break the word polynomial down, the word poly means many. So in geometry, you studied polygons, which were shapes with many sides. A polynomial means many terms. So let's look at some examples of polynomials. We have example 1, y equals -3 x squared plus 7x minus 4. This would be a trinomial because it has 3 terms, but it's a polynomial because it has many terms. What we want to be able to identify in polynomials is the degree of a polynomial. So the degree of a polynomial is determined by the highest exponent. So for this example, this polynomial would be degree would equal 2. Because I'm looking at this exponent right there. Alright, the other term that we're going to be talking about is the leading coefficient. So a coefficient is a number that's multiplied by a variable. And when we say leading coefficient, we mean the one that's attached to the highest exponent. Which if we write our polynomial in descending order will be the first one. But if the polynomial is not written in descending order, the leading doesn't always mean the first one. It's the multiplier of the term with the highest degree. So the leading coefficient in this example would be the -3. Alright, so let's just look at another polynomial. So I'm going to write it in function notation. G of x equals x squared minus 4x cubed plus 7x to the 5th. Alright, what is the degree of this polynomial?
5.
The degree is 5. It's the greatest exponent. And then what is the leading coefficient?
7.
I'm just going to put LC. We've written leading coefficient down once, right? So we'll just write LC. So the leading coefficient is the 7. It's the coefficient that goes with the x to the 5th power. It's not the coefficient that's just in front. Make sense? Alright, third and final example with degree and leading coefficient. What if I have this function, let's say h of x, it's written in factored form. X squared times 2x minus 4 times 3x plus 1. Now, if all I am interested is the degree and leading coefficient, I do not have to carry out that multiplication. So some of you started multiplying, just put that on pause. We don't have to multiply everything together. We're only concerned with the degree and the leading coefficient. So I'm just going to multiply x squared times 2x times 3x. Right? That's going to be one of my terms, and that's going to be the term with the highest degree. So x squared times 2x times 3x is going to give me 6x to the 4th power. 2 plus 1 plus 1 have x to the 4th power. Now, it's then going to be plus and minus some other stuff, but I don't need to know what those other terms are. What's my degree?
4.
My degree is 4. And what's my leading coefficient?
6.
6. All right. Besides just being able to say, look what I can do, I can tell you the degree and leading coefficient. Why would we care about that information? If we know the degree and leading coefficient, we know how the graph looks at either end. So we can, it's not just predict, because we can know the end behavior of the graph if we know the degree and the leading coefficient. So there's going to be 4 possible scenarios. So I'm going to come down here and I'm going to draw 4 coordinate planes on the paper that I have left. And if you want to draw them spread out on multiple papers, I'll be doing 4 coordinate planes here. So there's one. Here's another one. All right. So we're going to start with the parent function for a quadratic. We're going to start with f of x is equal to x squared. Right? We're real familiar with that function. We know that it's shaped like a parabola. We know that the vertex goes through 0, 0 because hk is 0, 0. We can plug in some values. 1 squared is 1. Negative 1 squared is also 1. If I square 2, I get 4. If I square negative 2, I also get 4. And so there is my parent function, y equals x squared. So what is the degree of this function? 2. Is 2 an even or an odd number? Even. So when we're looking at our degree, what's important is whether the degree is even or odd. All right, and what is our leading coefficient? 1. And is that positive or negative? Positive. So on the degree, we care about even versus odd. On the leading coefficient, we care about positive versus negative. We don't care about even and odds here. Every function that has an even degree with a positive leading coefficient will have this basic shape. Now, it'll do other stuff in the middle, but it will have this shape on the ends. It's called the end behavior. So, you don't have to draw this in your notes, but I could have some other function, right? And it could come here, and it could go all like this, go there. That's an even function. It's an even function with a positive leading coefficient. I know that. Do you see how it has the general shape of a parabola? It's got all this weird stuff going on in the middle there. We'll talk about that stuff later, but right now we're focusing on end behavior. Okay? And all the even functions are going to look the same for end behavior. Now, here's the part that may be new to you, which is how we represent this end behavior. So in the past, you may have just said that this side goes up, this side goes up. You may have even said this side goes to infinity. But we are going to use limit notation. So we're going to write like this. LIM, and then underneath that, x with an arrow, infinity, of my function f of x equals. So what is this saying? What does it mean? When I read it, I say this. I say, the limit as x approaches infinity, so that arrow is the word approaches, of f of x equals blank. Now what that means is that here on my x-axis, as I go out this way towards positive infinity on the x-axis, what is my function doing? Where is my output leading to? Way up here, where's that going? To infinity. Now last year some of you may have written as x approaches infinity, f of x approaches infinity with the little arrows. Limits, this is a very important concept and notation for calculus. So we're going to go ahead and pick up this notation here in pre-cal. Now, you can never equal infinity, right? You can't go stand on infinity. But this is not saying that the function equals infinity. It says that the limit of the function is equal to infinity. So its limit, that's where it's headed, that's its ceiling, so to speak, would be at infinity. Alright, so that's the end behavior to the right-hand side. So now let's look at the end behavior to the left-hand side. So we're going to write the limit, L-I-N for limit, as x approaches negative infinity of f of x equals. Alright, so what does this weird looking stuff mean? It means this. As we go out on the x-axis towards negative infinity, so x is getting smaller and smaller and smaller and smaller, what is the f of x doing? Well, here's my f of x. Look at where it's going. It's going up to infinity. And whenever you have an even degree with a positive leading coefficient, that's what the end behavior is going to do every time. Any questions there? Alright, let's slide over to our other graph. I'm going to label this guy g of x, and it's going to be equal to negative x squared. So we just finished our unit on transformations. What happens when you multiply by a negative in front of a function?
Reflection.
Reflection which way? Reflection over the x-axis. So this parabola is going to reflect over the x-axis. So it's going to have the same vertex, but it's going to go through 1, negative 1, and negative 1, negative 1, and negative 2, negative 4, and positive 2, negative 4, and it's going to go like this, right? A reflection over the x-axis. All right, so what is our degree? 2. Is 2 even or odd? Even. And what's our leading coefficient? -1, which is negative. So anytime you have an even function with a negative leading coefficient, your ends of your function are going to be falling, right? The function's going to be decreasing on the far left and decreasing on the far right. Well, how do we say that in function notation? So we're going to say the limit, LIM, as x approaches infinity of g of x is equal to negative infinity. So again, the meaning behind that, as x gets bigger, over here, where is g of x going? G of x is going down to negative infinity. Alright, then the limit as x approaches negative infinity of g of x. So, as this g of x, as my x values go over here, farther and farther to the left, smaller and smaller on x, what is happening to my output numbers? They are getting closer and closer to negative infinity. Every time you have an even function with a negative leading coefficient, that's going to happen on your end behavior. Alright, I'm going to switch colors for my other two. So now we're going to switch parent functions. Now we're going to go to the lovely x cubed cubic function. I'm going to say h of x is equal to x cubed. That's my parent cubic function. I know it goes through 0, 0. If I plug in a 1, 1 cubed is 1. If I plug in a 2, 2 cubed is 8. 2, 3, 4, 5, 6. Way the heck up there. But if I cube a negative number, negative times negative times negative is negative. So if I plug a negative 1 in, I'm going to get a negative 1 out. And my 8 is, negative 2a is going to go even off my graph. So it's okay. And I'm going to come in here. As you come this way, you need to make a curve. Right? None of it's linear. It's curved shape. Like this. That's our parent cubic function. So what's our degree? Degree is 3. Is 3 odd or even? Odd. And what's my leading coefficient? It's 1, which is positive. So let's talk about our end behavior. So the limit as x approaches infinity of h of x. So again, that means as x goes out this way towards infinity, as x gets bigger and bigger and bigger and bigger, my h of x values, my outputs of my function are going towards infinity. Meanwhile, my limit as x approaches negative infinity of h of x, so as we go to smaller and smaller x's, x goes out here to negative infinity, h of x, you see here, is falling down to negative infinity. And that's going to be true for all odd functions with a leading coefficient that's positive. Alright, we got one more to do. You can probably guess what we're going to look at here. I'm going to call this function j of x. Skipping over the letter I, because I is used for other stuff. You know what function we're going to write? Negative x cubed. So from transformations, if you multiply by a negative in front, what happens to the function?
Reflection over the x-axis.
Reflection over the x-axis. So imagine this function over here reflected over the x-axis. So this is going to reflect down. Meanwhile, this branch is going to reflect up. So it's going to go through 0, 0. But it's going to go through 1, negative 1, and then 2, negative 8 down there, and then negative 1, 1, and then 2, negative 2, negative 8. So it comes in here, curves, comes like this. So what's my degree? The degree is 3. 3 is an odd number. What's my leading coefficient? Negative 1, which is a negative number. So by virtue of that information, my limit as x approaches infinity, so my end behavior, so as x goes out this way, the j of x approaches or has a limit of negative infinity. And then over here on the left, my limit as x approaches negative infinity of j of x. So I'm looking as x gets smaller and smaller over here, going this way on my x-axis, my j of x, my output, is approaching having a limit of infinity. All right. We're going to pause for a second, turn and talk to your partner. One of you talk about the even functions, one of you talk about the odd. All right, so here's an example for us to try. F of x equals negative 5x to the 7th plus 3x squared minus 4. I want you to figure out the degree, the leading coefficient, and the end behavior. All right, so you should have gotten that your degree is 7, which is odd. Your leading coefficient is negative 5, which is negative. The limit as x approaches infinity of f of x is negative infinity. And the limit as x approaches negative infinity of f of x, that is going to be infinity. So let me give you one more to try. Write this down and pause the video and give it a try. G of x is x squared minus 4x cubed plus 5x to the 4th power. So let's look at the answers for this one. Shout them out. The degree is? The degree is 4. 4 is what kind of number? Even. Leading coefficient is? 5. That number is? Positive. Now, did anybody think the leading coefficient was 1? Why might a person think that? Because leading, and you think, oh, leading must be in the front, right? But that's not what this leading means. The leading coefficient is the one with the highest exponent. So then, it's an even, so that tells you both sides are going to do the same thing, right? So these are both going to be the same answer. And since it's positive, that means they're going up on both ends. So the limit is infinity for both of them. Got it? So now we're going to move on and talk about zeros, which are also called roots, right? And turning points. All right. So first of all, I just want us to have a picture of this. Like when you're talking about zeros and roots and turning points, Ms. Collier, where on the graph, what are we even looking at? So I'm just going to sketch a little graph here. Don't worry too much about where these points are, but I'm going to put a dot there, another dot, and another dot. My graph's going to go like this, and curve, and like this, and curve. Then it's going to do this at both ends, right? Might start off looking like a sine function, but it's not a sine function because sine function would keep going up and down. This one's going to ends. All right, so when I say the zeros, what do I mean? I mean these 3 points right here. Zeros, also known as roots, also known as x-intercepts, right? Why are they called zeros and why do we care? They're called zeros because there's some number for my input, but my output is 0, right? That's what makes them be x-intercepts and lie on the x-axis, because the output is 0. Why do we care about them? Well, think about in the real world what this x-axis might represent, right? If this is something that is in motion and it is actually physically going up and down, this x-axis might be the ground. And so these are the points where the thing is at ground level. Here it's below the ground. Here it's above the ground. We would want to know when it is at ground level, right? If our y value was the amount of money that we had over time, we might want to know when our money was at 0, when we were breaking even and having a profit of 0 versus times when we were making money, times when we are losing money, right? So the x-intercepts, the roots, the zeros, are usually of relevance to us when we're modeling a real-life situation. All right, so now what about turning points? This graph has 2 turning points. One is here, and one is here. These are called turning points. This is one of those nice times when the label means exactly what it sounds like it means. The turning point, it's the point where the graph turns. From decreasing to increasing, or increasing to decreasing. So after you've written those words down, let's look at what's happening. So here's my graph. And right here, right, my graph is decreasing, decreasing, decreasing. And now my graph turns and becomes increasing, increasing, increasing. And then it turns and becomes decreasing, decreasing, decreasing. So turning points are just points where the graph turns from decreasing to increasing. All right, so next we're going to learn about a little rule here. The degree of your polynomial helps you know about your zeros and your turning points. Now, it doesn't help you know what they are, but it helps you know how many there are, right? So think about if you were on a scavenger hunt and you're looking for something, and they just say, go out there and find some blue marbles. Well, wouldn't you like to know how many blue marbles are out there? Because, I mean, what if you find 5 and you just keep looking and looking, but there's only 5 to be found, right? So this little formula tells us the maximum number of zeros and the maximum number of turning points, so that when we find them, we know we're done. So if I have x to the nth degree, right? N is equal to the degree of my polynomial. Alright. Then I can have at most n zeros or roots. So if I have a 4th degree polynomial, the most zeros that polynomial can have is 4. It might have 3, it might have 2, it might have 1, it might have 0, but it's not going to have 5. The most it has is 4. And my degree is going to tell me that I have at most n minus 1 turning points. So whatever my degree is, I have 1 lower turning points. So if I'm on a 4th degree polynomial, that polynomial can only turn 3 times. Now it might only turn twice or once. Actually, it won't turn once. Because if it's even, it has to go the same way both times. But anyway, I guess it could turn once. Wouldn't turn twice. Well, it can if it's below the x-axis, I guess. Anyway, you have n minus 1 turning points. So, all this kind of gibberish that Miss Carly was doing in her head. Sorry. So, let's say I have some polynomial that's x to the 4th, blah, 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 right? So, it's got some other stuff added. How might that look? Well, it might have 4 x-intercepts. Almost kind of look like a W. But it might not, right? Might go up here and then turn and turn and then come up here, and now it only had 2 x-intercepts. So it doesn't have to have 4, but the most it can have is 4. Okay, next thing for us to do is to find the zeros. This is going to be a game we're going to play all next week. Find the zeros. We're going to start with the easiest way. The easiest way is finding the zeros if the polynomial is already factored. Okay? So this part is where the game's fun. Next week is where it will become frustrating. Maybe. I don't know. So let's say f of x equals x times x plus 2 and x minus 3. Find the roots, or find the zeros. So the roots, the zeros, that's when the output is 0. Right? So it's really saying 0 is equal to x times x plus 2 times x minus 3. And what we know from our fundamental theorem of arithmetic is that if these factors multiply together to be 0, then each factor might be 0. It's the only way you're going to get 0 as a product. So x equals 0. X plus 2 equals 0. X minus 3 equals 0. Subtract 2 from both sides. X is equal to negative 2. Add 3 to both sides. X is equal to 3. So there's my 3 zeros. X equals 0. X equals negative 2. X equals 3. That's all there is to that. Alright, so now we've got two things to do. First, we're going to do some group work on finding the end behavior, and then we're going to finish out our day working on IXL. The 2 lessons today, your SMART scores only need to go to 80.